Good morning, students. Topic of today's discussion is logic concepts and logic programming. Formal logic, it deals with the study of inference and it is synonym to symbolic logic. A symbolic logic is divided into two branches: propositional logic, predicate logic. Proposition refers to a statement that is either true or false, but not both. For instance, a sun rises in the east means it is true, or if I say sun rises in the west, it is false. It can be true or false. And we can infer new propositions from a given set of propositions. Suppose if I say that today it's cloudy, temperature is 15 degree. From these two propositions, you can infer the third proposition, which is it might rain. So new propositions can be inferred given a set of propositions. There are some features or properties that the logical system should possess. They are consistency, soundness, and completeness. Consistency implies that none of the theorems of the system should contradict each other. Two statements should not contradict. Uh, for example, John is suffering from COVID-19. This is one statement. Another statement is John has gone out to play cricket. Both are contradicting because when one suffers from COVID, one has to be home quarantined. They can't go out. That is consistency, which says that the system should not contradict each other. Soundness means the inference rules shall never follow a false inference from true premise. If the premise is true, inference should not be false. If it is said that the weather is very cloudy, and if it is a true premise, okay, sometimes it may not rain also. So then we can't be sure whether we can make a true inference from this premise. Okay, let us take another premise, which implies that John is suffering from COVID. Then the inference is he is home quarantine, and that is true. It is necessary to quarantine. So from one true premise, another true inference is made. Soundness implies that from a true premise, false inferences should never be made. If a system is sound and its axioms are true and theorems are guaranteed to be true, it means that the system is complete. And completeness means that there are no true sentences in the system that cannot be proved. Uh, Once it is said that John is suffering from COVID, uh, and we infer that he is home quarantine. This statement, which says that he has COVID, can be proved from the test result, which shows positive, which shows that he is positive to that. That is, we can prove the statement that he has COVID from the test results. All right, that is completeness. Completeness means no true statement in the system. In other words, every true statement can be proved in the system. All right. Further, there are two kinds of logics. The first one is propositional logic. Second one is predicate logic. Symbolic logic is divided into two branches: propositional logic, predicate logic. Propositional logic is the topic of next discussion. It refers to the language of propositions in which set of rules are used to combine simple propositions to form compound propositions. If there are simple sentences in English that we can combine to form complex sentences. For instance, mm, John is a boy. John loves cricket. And John plays cricket every day. These are three English statements, sentences. These are quite simple sentences. These simple sentences can be combined to form a complex or compound sentence. Instead of having these full stops and beginning a new sentence, we can combine saying that John is a boy, comma, he loves cricket, and place it. Place it means here it refers to cricket. Plays it every day. If you notice here, um these three simple sentences have been combined into one compound sentence. Likewise, simple propositions are combined to form compound propositions with the help of logical operators. What are logical operators and or not, logical operators? These are also known as connectives. Um, so the logical operators in the context of propositional calculus include not, and, or, implies, and equivalence. These are the five connectives. There is a need to understand what a well-formed formula is. Well, it is defined as a symbol or string of symbols generated by the formal grammar of a formal language. And the following are the important properties of a well-formed formula in propositional calculus. And what are they? The smallest unit is considered to be a well-formed formula. What might be the smallest unit? A simple sentence. Or a individual component, an atom, is a well-formed formula, alpha is a well-formed formula, then not alpha is also a well-formed formula. Well-formed formula is defined as a symbol or set of symbols that have been generated uh, from the language by following the rules of the grammar. If alpha and beta are well-formed formula, uh, then alpha and beta, alpha or beta, alpha implies beta, alpha equivalent to beta are all well-formed formulae. These are the three properties to denote a well-formed formula. What are the properties? The first one is it is the smallest unit. Is considered to be well-formed formula. Next, if alpha is well-formed formula, its negation, that is not alpha, is also a well-formed formula. If alpha and beta are well-formed formulae, formulae is the plural of formula. Um, Essentially, the sentences or the formulas that are generated by using the connectives are also well-formed formulae. Please remember this definition. Uh, we will come across to this in a further topic. What is a truth table? You have been learning truth table since a long time. It provides a definition of important logical operators and list out all the input variables and the output variable. The logical constants in propositional um, calculus. Propositional calculus are true and false. True and false are denoted by T and F. When you assume that A, B, C are proposition symbols of proposition, A is said to be well-formed formula. B is also a well-formed formula. Not A is also a well-formed formula. If A is well-formed formula, not A is also well-formed formula. When we talk about the truth table, apparently it is the application of all the connectives on the two variables A and B. Here these variables are propositional symbols A and B. You know, A and B, the same rules of truth table applies, and the same rules of the operators or connectives applies here as well. And means when both are true, it's true, otherwise false. When A and B are true, it is true. In all the other cases, it is false. Or B is A or B means it is true when any one of the statement is true. Otherwise, it is false. True is true. True false is true. False true is true, and false false is false. This is A or B. A implies B. In A implies B, if B is false and A is true, only in that case it is false. In all the other cases, the outcome is true. In equivalence case, when both are equal, the output is true. Otherwise, false. True, true is true. False, false is true. True, false, and false, true, false. Let us look at an example. Compute the truth value of alpha such that it is A or B and not A implies, not B implies A. Using truth table approach, this has to be evaluated or computed rather. A, B. You know the combinations true, 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 false, false, true, false, false. What is A or B? A or B is true in all the cases except when both the inputs are false. We got A or B. Not B is the complement of B. Not B implies A is when it is true, when not B is true and A is false. Only in that scenario, the output is false. In all the other cases, output is true. And what is alpha? When you combine A or B and not B implies A, when you combine with the AND operator, you obtain alpha. So true, true is true, true, true is true, true, true is true, false, false is false. So alpha is true, 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 false. Two formulae, alpha and beta, are said to be logically equivalent. This is the symbol. Alpha logically equivalent to beta if and only if the truth values of both are same. Consider that this is alpha, another one beta. Beta also, if you take some expression, when you use some expression for beta, then if um, alpha and beta results are same, consider B also. Beta also has true, 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 false. Apparently, it is said to be logically equivalent. Is this example clear, students? How to compute the truth value of alpha using truth table approach? Please note here that instead of using sentences, we are using symbols. Here the idea is to infer um, a, a conclusion. Make a inference from the existing facts. That is the idea of this logic concepts and logic programming. That can also be these all concepts can be studied uh, through the statements or the facts or the true premises. For instance, John is a boy, John loves cricket. This I can initialize to A. A is equals to John is a boy. B is equals to John loves cricket. If um, sentences are used, the whole study would become clumsy and complex. That's why we are using here these symbols instead of sentences or statements. The idea is to make an inference. How the AI system makes an inference from the existing premises. Premises are those sentences uh, that form the um, components of a propositional logic. Here, equivalence law, uh, with respect to this logic programming and logical concepts, it is commutative law. We know that already. We know this one. We say that A or B is equal to B or A. Here, uh, essentially, we are talking about the logical equivalence. That's why we are using this operator instead of this equal to operator. All right, these are logically equivalent, which implies that they generate the same result. A or B, uh, the result is similar to the result of B or A. Likewise, A and B is logically equivalent to B and A. Associative law. This one also you all are aware of. We can also put here plus and into or and or. In associative law, we know that A or B or C. B or C is within parentheses. When you put parentheses across A or B and take out C, when you do both the operations, they generate logically equivalent result, which means similar result or same result. And here, this is or, this is and. Double negation is equal to the original statement. Not A is A. Distributive law, in which when you expand this parenthesis, you get these two expressions, A or B and A or C. This one is A and B or A and C. De Morgan's theorem we learned. Now this one is and A or B is equal to sorry, this is not A or B is equal to not A and not B. Not A and B is equal to not A or not B. We know all these rules. Here the important idea to understand and learn is how AI system makes use of all these rules or laws in order to generate new sentences or inferences. This truth table shows the verification of uh, A or within parentheses A and B is logically equivalent to A. This is the expression given. To prove that this expression is true and valid, a truth table approach is used in order to prove that uh, this statement is true. A is true, true, false, false. Here B is true, false, true, false. A and B is true, three false. A or A and B is true, true, false, false, which is identical to A. So hence it is proved that this statement is logically equivalent, these two. All right, this is all about truth table approach. Using truth table approach also, AI system can make inferences and generate new statements by making use of all the rules that have been discussed. Propositional logic. In propositional calculus, all the uh, rules with respect to that logic is studied. We have seen what are symbols, what are connectives, and how statement symbols are connected, and what is well-formed formula, and what are the properties of well-formed formula. These are the topics that have been discussed under propositional calculus. Propositional logic deals with validity, satisfiability, which is also known as consistency, and unsatisfiability, which is inconsistency of a formula, and the derivation of new formula using equivalence laws. In under propositional calculus, equivalence laws have been defined. Using those laws, how new formula can be derived and how the consistency or inconsistency and validity of a formula can be understood and uh, can be defined. In a truth table, each row for a given formula alpha is called interpretation, under which the value of the formula may be either true or false. All right. If I say that uh, Earth is a planet, Earth is a planet, if this is a statement, based on its interpretation, its meaning, based on the semantics of this formula, it can be either termed as true or false. All right. First, the formula has to be, uh, understood, or its semantics have to be clearly defined, or it should be clearly interpreted. When it is done later, uh, it can be uh, either defined with a value true or with a value false. A formula alpha, and you can use alpha for this statement. Instead of writing a certain statement, use a symbol to denote it. A formula alpha is said to be tautology. Tautology. If and only if alpha is true for all its interpretations. You take this sentence and you ask anyone, everyone interpret it to be true. In that scenario, it is said to be tautology. Tautology means when it is true under every circumstance, under every interpretation. And validity, satisfiability, unsatisfiability of a formula is determined based on the conditions. These three. A formula alpha is said to be valid if it is a tautology. If it is a tautology implies if it is true under every interpretation. Um, people belonging to different regions, different states, different countries, everyone says Earth is a planet. Then it is a tautology. A formula alpha is said to be satisfiable if there exists at least one interpretation for which alpha is true. Um, if I say that John is uh, a topper, if I say John is a topper, there are different interpretations. I may be uh, calling him topper if he gets a rank of 1, 2, or 3. Okay. If he belongs to rank number 1, 2, or 3 group, anyone, I am calling him topper. But there might be someone else who calls him topper only if he obtains rank number 1. There might be someone who calls him topper if he is under rank 10. Okay, there is no clearly defined um rule that a person cannot be called a topper if he uh, unless he get a first rank. All right. So any one interpretation is true. Then the formula is true. I mean formula is satisfiable. A formula is said to be unsatisfiable when uh, formula is false under all interpretations. Whatever may be the interpretation made, it is evaluating to false only. Under that scenario, that formula is said to be unsatisfiable. With an example, let us discuss. There is a argument. If it is humid, then it will rain. Okay, then it will rain. And since it is humid today, it will rain. Students, can you identify here the statements and the inference? What are the statements and what is the inference? Yeah, can anyone please try to at least make a guess? What is a statement and what is the inference? All right. Well, here A and B. It is humid, it will rain. These two sentences are denoted or symbolized by the symbols A and B. And the inference is it is humid today, it will rain. Actually, it will rain. The formula alpha corresponding to the given sentence, how it can be written? A means it is humid. B means it will rain. And this is implies operation. If then. Implies operation is also known as if then. If it rains, if it is humid, then it will rain. And it is humid. What does it implies? It implies that it will rain. This sentence is symbolized in this manner. A implies B and A whole expression implies B. When when various combinations are taken up in order to check whether this interpretation is tautology or satisfiability or what, or whether it is a valid argument. A, B, A implies B, which is symbolized as X. X and A symbolized as Y. Y implies B. See, under all circumstances, under all interpretations, all the combinations, it is generating all truths. When it generates all truths, what does it mean? It is a tautology and it is a valid argument. All right. Uh, the other methods to prove the correctness of a argument with proofs and deductions are natural deduction system, axiomatic system, semantic tableau method, resolution refutation method. These are the four methods that are concerned with proofs and deductions. Whether whether we can conclude that an argument is valid or not. Using truth table approach is simple, however, it is wastage of time. It is wastage of time as it takes, more amount of work here. You see, we have to list out all the combinations for all the symbols and check upon this. For two variables, it is fine. For three variables also, it's okay. But then if the symbols are more, if they are five or six, then these combinations would be more. Therefore, you can resort to other methods which are natural deduction system, axiomatic system, semantic tableau method, resolution refutation method. The first one, natural deduction system, is about uh, mimicking the pattern of natural reasoning. What is natural reasoning? How humans perform the reasoning. And this system is based on set of deductive inference rules. Assume that A1, A2, A3 up to AK, where 1 is less than or equal to K, which is less than or equal to N, are set of items, and alpha J, where J is greater than 1, greater or equal to 1, and less than or equal to M, and beta are well-formed formulae. Alright, these are well-formed formulae. Then how inferences can be made? For that, there are rules. This is the rules table. Introducing, uh, this is what, and. And when you are introducing and, the symbol is, this is I colon and, means introducing and. Rule is if A1 up to AN, then A1 and A2 and up to AN. There are these formulae. Each one is one formula, A1, A2, A3, A4, up to AN. These are all formulas. When you introduce uh, and in this, they would um, combined using this and operator, connected. A1 and A2 and like that. What is the description? If A1 up to AN are true, then their conjunction is also true. If every uh, formula in this is true, then their conjunction is also true. Eliminating and E and symbol. When A1 and A2 and up to AN is true, and these ands are eliminated, individual formula is also true. Here, when you observe, individual formula are true. Every individual formula is true. When you combine them, uh, we get a combined true formulae. Here, when a combined true formulae is true, the individual formula is also true for every individual formula. Introducing all, 1 minute, students. Okay, students, sorry about this. Moving on to this next rule, introducing or, this is also similar. There are formula, you know, A1, A2, A3, these are formula. Ha- Again, please recall like this. A. A can be some sentence, some statement, and A can be called as a formula. It is actually a symbol that denotes a statement. Okay, introducing or, eliminating or. All right, eliminating or. When you eliminate or, then individual formula is true. Introducing implies. And when you introduce implies, if given alpha 1, alpha 2, and alpha n are true, and from these we deduce beta, then alpha 1 and alpha 2 and alpha uh, n implies beta is also true. If there are these formulae alpha 1, alpha 2, alpha n, and all are true. Consider that from these formulae, beta can be deduced. Deduced means derived. Like how here we are deriving it will rain. Here we are deriving it will rain. How we are deriving it will rain? From these previous statements. When you introduce this implies, then all these formulae joined by and operator implies beta is true. Likewise, eliminating implies is there, introducing equivalence, eliminating equivalence, introducing not, eliminating not. This all means the same. Same in the sense that when you have individual formulae, when they are combined with certain connective, if individual formulae is every individual formula is true, after combining also it is true. The merged formulae is also true. All right, students. Now this is the example. Prove that A and B or C is deduced from A and B. This A and B is there, existing one. We have to prove that we can deduce, means derive A and B or C from A and B. Through natural deduction system, this natural deduction system, which is the first method uh, for this logical reasoning, here we can see the proof. This the description column, formula column, comments. Theorem is from A and B infer A and B or C. And what is hypothesis? Means whatever is the given formula. Given formula is A and B. Here E and 1. 1 is here, 1 is the expression number. From 1, eliminate and. After you eliminate and from 1, you get only A. From A and B, after eliminating and, it's just A. And eliminating and on 1 again gives you this side. If you eliminate B, only B. All right. I means introduce, introducing or. We are introducing or on the formula number 3. On the formula number 3, when you introduce or, it becomes B or C. When and is introduced for formula 4 and formula 2, between them when and is introduced, we get A from here. A and is introduced and B or C is from formula 4. Therefore, it is proved that A and B or C can be deduced or derived or inferred from A and B. This is another theorem. Prove the theorem and infer this one. Students, Is this clear? Anyone can state this, how to prove? No? All right. To prove this, A implies B and B implies C. A whole expression implies A implies C. This is the theorem. What has to be inferred? A implies C has to be inferred. From A implies B, B implies C. From this to here, A implies B and B implies C. A implies C has to be inferred. For that, there is hypothesis 1, A implies B. Hypothesis 2 is B implies C. And this is the sub-theorem. The sub-theorem is that inferring C from A. How to infer C from A? The hypothesis is A, just take A, and E, eliminate implies from 1, comma 3.1. 3.1 is this, 1 is this. You get B. Eliminate implies 2, comma 3.2. 2 is this, 3.2 is B. So you obtain C. And these are formula number 3.1, 0.2, 0.3. And when uh, implies is introduced on this uh, formula number 3, on this 3.1 and 3.3, you obtain A implies C, which proves that A implies C can be inferred from this. All right, students, hope the class is, it makes sense. Anyway, please go through it. If you have any doubt, you can ask in tomorrow's class.